So I figured.
Welcome to Geometry Honors.
I figured when somebody's absent and we're doing an important lesson, I'll try to make sure that I do a screencast. So if you're absent and you want to watch it later, I'm not saying I'll do it on every lesson, or maybe if it's a real difficult lesson, I can also do that.
Hi, Brittany.
Yeah, hope Brittany feels better.
Hello.
Okay, so
Feel better.
the Pythagorean theorem is something that you guys have definitely seen before. Again, it's part of the Algebra 1 curriculum, which is one of the reasons why we've had it in certain spots throughout the first and second semester. Yeah, I know, it was on the last test when we had a rhombus or a square. Their diagonals are always perpendicular. So whenever you have a right triangle form, okay, so that's number one. You gotta have a right triangle. If you don't have a right triangle, you cannot use the Pythagorean theorem. If you have a right triangle, the Pythagorean theorem will always apply. So it just says the sum of the squares of the legs equals the square of the hypotenuse. Or we know a squared plus b squared equals c squared. So this, we just need to make sure is our hypotenuse. Remember, the hypotenuse is always opposite the right angle.
Does C stand for chi? Do you know chi-square? Observed minus expected squared.
Just shut up.
No. Okay. All right, guys, so let's take a look.
Why does it only work for right triangles?
What's that?
Why does it only work for right triangles?
Try it on a non-right triangle. I bet you.
It will not work.
Okay, so why does this only work on right triangles? Well, first of all, it's based on having a hypotenuse, and you can't have a hypotenuse without a right angle. So we're going to actually apply the kind of a form of the Pythagorean theorem to see if we have an acute triangle or an obtuse triangle. But if it's equal, it has to be a right triangle. Okay, we'll actually look at that later. So the first thing I would like to do is actually prove the Pythagorean theorem so we're specifically using geometric means. It's actually not a difficult proof. It's all algebra, okay?
Yay.
So the one thing that we have here is that we have our triangle. Here's ABC with a right angle at C. And then you'll notice that a number of these sides are labeled H for kind of like the height of the triangle, the altitude here. X and Y are representing segments of the hypotenuse. A and B are the legs, and obviously we can see that C is the entire hypotenuse. Are we following so far? Okay, so we want to try to prove that it's a squared plus b squared equals c squared is always going to work. So what we want to do, using geometric mean, let's think about how can we set up, we're actually going to set up two proportions based on what we know about the altitude and what we know about the legs of a right triangle. Any ideas? Go ahead, Sarah.
Y over H equals H over X.
What are you doing?
Okay, here. The H is fine. It's just we want to work with mainly the A and the B.
Oh.
Can I try again?
Trying to do you see? We're trying to get a squared plus b squared equals c squared. So if I can get them equal kind of to the same thing. You want to try again, Sarah?
I want to repeat this.
Okay, go ahead.
Okay. A over right.
Okay, so A is the leg.
A is the bottom.
C over H.
C over.
So the leg is the geometric mean. So A goes here and here. Honestly, it doesn't matter if you put them here and here. It's fine. It would be the same idea.
It would be Y and C.
Would it be Y and C? You guys agree? Yeah.
I was going to say that.
So we had two theorems. One regarding the altitude of the right triangle is the geometric mean between the two segments, so that would be x and y. And then we had one based on the leg. The leg of a right triangle is going to be the geometric mean of the hypotenuse and the segment adjacent to that leg. Now I want to also put another proportion together based on the other leg, b.
Wait,
Just-
is,
Oh,
Sorry.
C over B equals B over X.
Good.
Yeah.
We're okay with that? All right. Any questions?
I don't understand this.
Should have gone to the lesson yesterday.
Okay.
It's content.
All right, let's cross multiply. So we get a squared equals c times y, right? And over here, we get b squared is equal to c times x. Yes, and that's actually what we're going to do in the next step. So we want to take these two results and kind of put them together. Remember, what do we want to end up with? We want to end up with a squared plus b squared equals c squared. So, can I add two equations together? Yeah. I can take a squared plus b squared. So in other words, I'm going to take the left sides of both equations and add them together. And then I'm going to put what's on the right side of the equation. So that's going to be equal to cy plus cx. That's all. We've added the same thing to both sides of the equation. We've basically said this plus this has to be this. That's addition property of the column.
How do you do CA equals A over y?
A is the geometric mean of the hypotenuse and the segment adjacent to it.
But C is not Pythagorean, so.
The leg. Let me go back just 1 minute. Those of you that want to continue on, factor out a C on the right side and see if you can get factor out C on the right side. Okay. Theorem 8.3 says any leg, so a leg of a triangle is the geometric mean, so that means you put the leg here and here, between the hypotenuse and the segment adjacent to that leg. Okay, so when we look at this, A is a leg, A is a leg. C is the hypotenuse, Y is the segment adjacent to that.
Wait, what triangle are we looking at for the whole?
Okay, we always look at the big triangle. So if when I say a leg, I'm talking about a leg of the big right triangle.
Oh, I thought you were talking about that small piece.
No. No. All right, now, did everyone see that you both have a common factor here of C? I told you, factor out C. Well, now, what did Danny say? Danny said, well, can we just replace x plus y is equal to C? Do you agree? X plus y is the same thing as C.
Whoa.
So we have a squared plus b squared equals c times c, which is really a squared plus b squared equals c squared.
That's a lot of work.
That's a lot of work. It's two
without
proportions.
Math with letters.
I think letters make it.
Wait,
I
I lost my
pencil.
pencil.
Let's see what C times C is.
No, letters.
You cancel out the letter into X.
X plus y is the hypotenuse.
So what you're saying is A plus B.
All right, questions on that one?
And the next ones are just regular. Just like
Bingo!
Okay, so example 2, we just want to apply Pythagorean theorem. Of course, we don't always have whole numbers. Sometimes we have radicals to work with. A is, B is really easy. Now, does it matter which one we make A and which one we make B?
No.
No, as long as we make sure that, right, X is going to be our hypotenuse. So we have 37.5 squared plus 20 squared equals X squared. No, it is.
1,406.25.
Is it?
It's not on it?
It's
1,406.25.
Wait, what's the
So-
answer?
so
People are
it's a-
saying like.
1406.
Oh, you said 14.
No, 37.5 squared is 10406.
I don't know how to take the
Sorry, it's
that.
called the knowledge.
Can I just,
42.5.
can I make it a decimal? Does it have to be a radical?
42.5 is the answer. I
So
think.
when you take the square root,
Does it have to be, or no?
well, this one comes out, if you have your calculator, this one comes out exact.
Where do you take one?
So when I take the square root, now we don't want plus or minus here. Why don't we want a plus or minus?
There's you can't have a negative sign.
Right, we don't want to have a negative length for a side. And assuming, sometimes you could have an actual negative value, as long as you plug it back in and you get a positive length. But here, it was just x, so we just want to make sure that it ends up being positive.
Well, B is really easy.
Okay, b is really easy because x squared plus 6 squared equals 10 squared.
I don't do it. Can you do? I just do 10 squared minus 6 squared equals 5 squared.
Say that
Way
again?
to undercomplicate things.
It's not hard.
Say that
That's
again,
exactly
Summer?
what it is.
Excuse me.
What was your question?
Yeah, I'm sure kids like to use what they were taught.
No. You like you.
All right,
Yeah.
moving down. We're okay with that? Okay, let's do one with fractions.
Can you just multiply everything by 7 instead of 7?
Okay, when we, I want you to be able to do this with finding the exact answers. So this is why we were working with the square roots yesterday, and we had some review of it before. So when we square a fraction, we square the numerator and we square the denominator. So we get 16 over 49.
Do we have a
And over here we
simplify?
get 25 over 49. So when we subtract, they already have a common denominator, which is nice. So subtracting, we get 9 over 49. And we talked about when we take the square root, when you take the square root of a fraction, you take the square root of the numerator and the denominator, which works out because they're both perfect squares, so you get 3 over 7.
Is it going to be this nice?
No.
Nope.
Wait, don't move that.
Maybe.
Wait till the last lesson of the chapter. It'll be way times
square root of
49.5 is 62.
What?
Well, if it's
Hi,
7
Brittany.
is wrong, it's 7.5.
Hi, Brittany. Wait, don't move. See, I told you to get harder.
What?
Okay.
The
Oh.
next couple lessons.
Okay.
All right, so the converse of the Pythagorean theorem. So basically says if you have the sum of the legs,
So katoa.
so if you have the sum of the squares of the legs equal to the square of the longest side, then it has to be a right triangle. So it's basically saying if a squared plus b squared equals c squared is true, then we know that triangle ABC is a right triangle. It's usually when the battery goes back. No, it's usually when the battery.
You Dawn, what did you do?
How do we know which one's C squared if there's no rating?
How do we know? What's it saying here? It says it has to be the longest side. So hopefully you can pick which number looks to be the longest. Does that make sense?
Maybe,
So that triangle has to be a right triangle. So in this next example, as Sarah was just asking, how do we know which one? Because it doesn't, you can look at the triangle and see maybe which one looks like a right angle, but don't assume that. You always want to make sure
Do we test all sides?
this is the longest side here. How do I know that that's the longest side? Just by looking at the
because
numbers.
64 is 8 and
Right.
8 is more than 6 and 5.
Well, 6 is the same thing as square root of 36. 5 is the same thing as square root of 25. So obviously the square root of 61 has to be the largest.
Also, it's a cosine.
Well, we don't know. What we're going to see is that a right, that's what we're trying to test for. So we're basically saying this is going to be equal to C. So I want to see is 5 squared plus 6 squared, is that equal to square root of 61 squared? So we get 25 plus 36. And then we know when we square a square root, they just cancel. Right? It cancels out that square root sign. And they equal each other. That's what we wanted
So
to
if they're
check
equal,
for.
we know for sure that it works.
Right, so this one is yes. If one side ended up being 60 and the other one ended up being 61, it's close to a right triangle, but it's not. They have to be exact. Okay, this one, again, this has to be our longest side because square root of 11 is a lot smaller than square root of 49, which is the same thing as 7. So I want to see is 5 squared plus the square root of 11 squared. Is this equal to 7 squared?
No.
So we get 25 plus 11. What do we get on the left side?
36.
36.
No.
So this one is no.
I took it a step further, just some 6 equals 7.
Yeah, I see what you're saying. Any questions there? Okay, so the next page is on Pythagorean triples. So Pythagorean triple just means that they're whole numbers that satisfy a squared plus b squared equals c squared. So if they're all whole numbers, then we know it's a Pythagorean, we just call it a Pythagorean triple, which means if those were the lengths of 3 sides of a triangle, it would have to be a right triangle. So an example would be a 3, 4, 5. Can you think of any others?
8, 15, 16.
You think 8, 15, 16?
Yeah.
8, 15, 17.
I'm guessing.
20, 48,
Let's see.
8, 15, 17.
We just did one up here. Example 2b. This turned out to be 8.
8,
So 6, 8, 10 is another example of a Pythagorean triple. I will say that this one is not a Pythagorean triple because they have fractions.
So if it's a fraction?
So if it's fraction, then
What
it's...
about
So if it's a fraction, it could still be a right triangle, but we don't call it a Pythagorean triple. So there are 2 parts to the
So
question that we're looking
A
at.
is incorrect.
Okay, so there's 2
Not a
questions.
Pythagorean triple.
There's one is, do they form a right triangle? So that just means,
It was no.
A squared
I
plus
know.
no.
it just means if a squared, let's see if it'll work, plus b squared, sometimes then the battery runs slow too. And then the second part of the question, is it a Pythagorean triple? So if the first part's true, and you have 3 integers, then the second part is true.
First part's not true, and then it's
Do you see what the question's asking? Okay, so let's take a look at the first one. So 8 squared plus 15 squared. They're not equal to each other? Or they
No,
are?
it's not triple.
It's not. So you get 289 here, which is not equal to 256. So no and no. Not a right triangle.
No.
So basically, if the first part's no, the second part has to
Wait,
be
what
no.
does the second one mean? Like, what does a no mean?
Okay, so the first part, is it a right triangle? The Pythagorean triple part would be if the first part is yes, and they're all whole numbers. Pythagorean triple are whole numbers. They might be whole numbers here, but they don't form a right triangle, so they cannot be a Pythagorean
So
triple.
those are automatically null.
Right, so in part B, I can already tell the second part is no, but it's the first part, yes. So we want to see, and just double check, sometimes they're not in the right order. Would you agree that 3/5 is the largest side? If you're not sure, could you plug in square root of 3/5 and square root of 6/5 and actually compare the decimal approximations? You could. So when we square, be careful in this one because when we square the numerators, sometimes, yeah, you want to square the numerator and the denominator. Some are under radicals, some are not. So this one will just be 3, but the bottom will be 25. And then the next one, the square root of 6 squared would be 6, but 5 is not under the radical, so we square it. And then here, neither the numerator nor the denominator are under a radical, so we square both of them. So we get 9 over 25. So yes. Right.
Yeah.
So would you like a comma or a semicolon?
Semicolon.
Apostrophe.
Semicolon. Separate thought.
Okay. Semicolon, separate thought?
Yeah.
Sentence.
Yes, and then no. All right, questions? And then C and D, and I'll take a volunteer. You want to do C? For some reason, and then Danny, you would do D? Oh, sorry. And for some reason, the tablet's not working, so you got to do it on the board.
The board doesn't like me though.
Just try.
Can I do the tablet or does it not?
It's not, I don't, sometimes every once in a while, it doesn't, the pen doesn't work. So,
Oh, Windows.
In this case,
it's just, it's because my laptop's just old.
I blame Hewlett.
in this case, so the first
It's
part,
It's Toshiba.
Oh, it's
It is Toshiba?
I blame Japan.
There you go.
global warming.
What was the question?
if the first part is yes and they're whole numbers, then is the second part?
Yes. So part C, so Sarah's putting that one up. Do we get an answer of yes for the first part?
Mm-hmm.
Okay. And then,
Yes. Semicolon.
But it-
I said 20.
yeah, at an angle. It's when this doesn't read properly. So if the first part is yes, and you see that you have whole numbers, automatically the second part is yes. You have questions on the homework exactly like this. They're set up in the same way.
Wait, the D didn't just do like the whole 7 and you can't fall.
Yeah, so you might be able to tell some of these just by looking at them.
It likes me. Usually the board does that for me.
You
Every board I do
I
it
know.
on.
It's
Every
like-
single time. And then this time I
try it like from an angle, but don't hold it. Like when you hold it too close, it makes it look tiny. That's like it takes practice. I'm telling you, it's a crazy thing. I wish it worked. All right, and then what do we get for the next one? Okay, so we have about 7 minutes.
Clapping.
While Danny's finishing up.
I second the nap time idea, whoever thought of that.
Wait, why can't
Ari, was it you?
Those of you,
Danny, you're a natural.
thanks guys.
Danny, tilt the pen up more. I don't know.
No, like
am I right?
writing
or am I
like
wrong?
when it's going
You
straight.
don't, you don't want to make it like perpendicular to the board.
Oh, then never mind.
See, then it has trouble reading. See how it has trouble reading? It's kind of strange.
So it has to be at an angle?
It has to be like an angle.
45?
We should use a wheel
And you
ball
don't want to
point
block,
and
you don't want to block the view.
board.
It's not sledding, it's just sled. There's one called
You know,
sled.
since class is over, basically it's good night.
Yeah,
I
but-
said
5
Flappy
minutes.
Birthday.
Alright.
Flappy birthday.
It's just giving you.
Happy birthday